So last class we discussed thermal energy, and we said that when a hot and cold object were brought in contact with each other, thermal energy would be transferred from the hotter one to the colder one. Well, what are the physical mechanisms by which this thermal energy is transferred? It turns out there's three. There is conduction, which is transfer by direct physical contact. You put them touching each other. Then there's convective transport, which is transfer of thermal energy by a moving fluid. So, for instance, you warm up some air in your furnace, then you blow it with the fan, and that takes thermal energy to all the rooms of your house. Another example in the biological context is you do some exercise, that warms up your muscles, the blood flows through your muscles, absorbs that thermal energy, and then takes it to your skin for dissipation to the environment. Finally, there's radiative transfer, which works through the vacuum of space, and that's transfer by electromagnetic radiation. And typically, for most temperatures of interest the electromagnetic energy is going to be mostly in the infrared part of the spectrum. So those are the three means of thermal energy transfer that we're going to look at in this class: conduction, convection, and radiation. We'll start with conduction. We'll start with Furius Law of conduction. And what Furius Law says is that we analyze, say, the flow of thermal energy through a slab of material. And Furius Law says that the thermal energy flow through that material depends on a few things. First of all, it depends on the temperature difference across the material. That's delta T. So with a greater temperature difference, you get more thermal energy transfer. It depends on the area of the slab A. With a greater area, you get more thermal energy transfer. It varies inversely with the thickness, because a thicker material has a smaller rate. That's inverse variation. I'll use D for thickness because I'm going to have T for time and T for thickness, and T for temperature, rather. So I'll use D for thickness. The last thing that influences this is the material. And there's a constant known as K, which is the conductivity, and the rate of flow of thermal energy varies directly with that conductivity. So let's build Furius Law. It says that the rate of thermal energy transfer, which is the ratio or the amount of thermal energy transfer per unit time, varies directly with, as we just discussed, the material's conductivity, the area of the slab, the temperature difference across, and inversely with the thickness. And these are all the units. The units of these three quantities are familiar to you. K is joules per second centigrade meter, or you can write it as watts, because a watt's a joule per second, per meter Kelvin, because a temperature difference of a degree centigrade will also be a temperature difference of a degree Kelvin. Now, this is a rate of heat flow. Recall, for fluid theory, we defined the volume rate of flow as being cross-sectional area times the speed, and that was the ratio of volume to time in cubic meters per second. This is a similar rate of flow, but it's the joules per second of thermal energy flow. So that's our first principle for today. It's the principle of conductive thermal energy transfer through a slab of material. Now let's talk a little bit about the thermal conductivity K. So if K is big, that's a good conductor. So what's an example of a good conductor of thermal energy? Well, that would be something metallic. That's why we make pots out of metal. If K is small, then we're dealing with something that's an insulator. That may be, say, like a piece of foam, or body fat is a good insulator. So we can mix and match here. We could say K for steel, that's a conductor, it should be big. K for fiberglass insulation, that's an insulator, that should be really small. And then the K value for glass, well, that's probably in between. And so these are some typical values, and we will use values like this in the problems that we're going to be solving today. So here's a typical example. So we've got a stove element on your stove, and you're putting a pot of water on it. And thermal energy is going to flow through the bottom of the pot into the water, And we're boiling the water. And at STP, boiling happens at 100 degrees. And we're told the element's at 220. So we see what the temperature difference is across the bottom. Now, the bottom is going to be circular in cross-section. So we've got pi r squared for that area. So we want to find the rate of heat flow. So that's the amount of joules per second of thermal energy flow. That's conductivity, area, temperature difference divided by thickness. So it's steel, so we look back at the previous page and say that was 80. 80 watts per meter Kelvin, or 80 joules per second centigrade meter. Cross-sectional area is pi r squared. R is the radius of the pot. That's given as 10 centimeters. And then temperature difference, we said, was 120 degrees centigrade, or 120 Kelvin, divided by the thickness, which is 1 centimeter thick. And then this is the rate of thermal energy transfer. Now, as the thermal energy comes into the boiling water, it's going to produce steam. And we know that the amount of thermal energy, or rather thermal energy that's making steam, is latent heat, and is therefore given by this relationship here. So, just delete that email there. If we want to find the rate of production of steam, that means we want to know the mass. The latent heat is going to be 2,256,000 joules to vaporize a kilogram. So we'll find the joules per second and then put it in here, and then we'll solve for the mass. Let's just pause and I'll work that out. So we see that the amount of thermal energy transfer is 30,159 joules each second. So in 1 second, it's 30,159 joules. We divide by the latent heat, and then this will tell us convert from joules per second into kilograms per second. So it's 0.13, or it's 13.3 grams per second. And so that's the amount of steam that we're producing. So we know there's 30,000 joules going into the pot each second, so that tells us that 13 grams of steam are being produced. Next example, this is an interesting one here for historical reasons. Kelvin estimated the age of the Earth by imagining that the Earth had started off as a ball of molten rock and had gradually cooled. And so in his mind, there was a layer of crust on the top, and then at the center there was this layer of molten rock. Now, he knew the temperature at which rock melted. He knew it was 1200 degrees. He also knew from coal mines that the temperature dropped at about per 100 meters, about 2 degrees. So that's about 0.02 degrees per meter. So based on that, he was able to work out what the depth was, or what the thickness of the crust is right here. That's D. So this is basically at 0. This was 1200. If it's 0.02 degrees C per meter, and if we've got to reach 1200 C starting at 0 C, what was the depth of the crust? Let's call that the depth of the crust. So cross-multiplying, we see that it was about 60,000 meters, or about 60 kilometers of crust, and that's not far wrong. That's a pretty reasonable estimate. So next he said, all right, well, if we started off, so this is the 60,000 meters we worked out, by the way, if we started off then with a totally molten Earth, and we've ended up sometime later looking like this, how much thermal energy has been lost to space? So he said each one of these layers of rock at a given depth, right, and say we're at some depth that's less than the 60,000, it's cooled down from 1200 down to its current temperature. So that is the temperature change of a given layer of rock. And then the ones that are deeper haven't cooled down as much. The ones at the surface have cooled down by 1200. So this is the delta T for that layer. And we're going to say the thickness of the layer is delta D. There's a little delta D. Okay, so for that layer, this one layer here, its amount of thermal energy that has been lost out into space is going to be the mass of the layer times the specific heat capacity of rock times the temperature difference. But for that mass of a layer of rock, a mass is a volume times a density. And the volume of this little slab is going to be the surface area A times the thickness delta D. So for our Q equation, I'm not going to put it there, I'm going to put it here, it's surface area times the thickness times the density of rock, that's the mass value, and now we've got to put in the specific heat of rock and the temperature difference. Now if we rearrange that just a little bit, we've got A, the surface area, rho, the density of rock, C, the specific heat, then we've got delta D, delta T. And if we look on our picture, delta T, delta D is just the area of that little wedge that we drew on there. And we want to, of course, find the total temperature difference, not just for this one little layer, but, the total energy, not for just this one little layer, but for all the layers of rock. That means we want to add up all of them. So we'll do that by summation. So we're adding up, what was that? That was A, rho, C, delta T, delta D, over all the layers, and I'm using summation notation here. But A, rho, and C are just constants. They're the same for each layer, so we end up adding up delta T, delta D, and as I said earlier, that's the little area of that little wedge. And if you add up all those little layers, then you end up essentially just finding the area of this triangle, right? Because you'd be adding up this little area, adding up this little area, and that's going to give the area of the triangle, which is half times space times height. So we end up with A, rho, C, then 1/2 the temperature, temperature of molten rock, and then the depth of the crust. So this is 1200, and that's the 60 kilometers, and they're constants. So that's the total amount of thermal energy that's left the Earth as it has cooled down from the molten state. Well, now we could use Furius Law, and we could say we know how much thermal energy is left. We'll assume that rate's been constant. We know the thermal conductivity of rock. We should be able to solve for time. And this ratio right here of temperature change over distance, that is just that thermal gradient that they found from coal mines, that for every 100 meters, it went about 2 degrees centigrade of temperature increase. Okay, so we can solve then for time t, which is the age of the Earth, by cross-multiplying it up and by cross-multiplying these things down. So this is going to be K, A, and then the temperature gradient, delta T over D. Now the Q constant we got from the other page, that's all the thermal energy that left the Earth as it has cooled down. And then the denominator here is the same. But the interesting thing here is surface area just cancels. We know all these constants now. And so we could substitute in rho, the density of rock, C, the specific heat of rock, the 1200 centigrade, the 60 kilometer depth, the thermal conductivity of rock, and the temperature gradient of 0.02 degrees centigrade per meter, and we can work out the age of the Earth. So I'll punch that through, and then we'll see what we get. Okay, so substituting in all the values and the various units, we end up with 960 trillion seconds, which is about 30 million years, which is a significant amount of time, but it was thought not to be enough time for Darwinian evolution to occur, and as a result, this was used as evidence against Mr. Darwin's theory. Of course, what Kelvin had missed in this calculation, the age of the Earth, was the convective energy transfer, and a better calculation where you assume that due to convective energy transfer, that you've got a shell here that's fairly thin, and then you've got a core that is basically at the same temperature, that has been cooling down from some initial temperature T down to its final temperature, with convective currents there ensuring that the temperature is constant. If you do that calculation, you get a much older age for the Earth, on the order of billions of years, which is enough time for Darwin's evolution to occur. But anyhow, this just shows you, this is physics from 150 years ago or so, mid-1800s. This just shows you that with the fairly simple Furius Law of conduction, you can come up with an interesting result, which is the age of the Earth. Biological question, why do animals huddle when it's cold outside? So here, this is a rear view of a cow. So this is in the summertime. In the wintertime, they get much closer together. Why does that make sense? Well, with less exposed surface area, the rate of thermal energy transfer, which depends on the exposed surface area, there's a lower rate of energy loss to the environment. That's why. So having spent some time looking at the conduction of heat, we next look at another means for transferring thermal energy, convection. Convection occurs when thermal energy is transported by a fluid, say moving air or a moving liquid. An example would be in the human body. When our muscles do work, they generate thermal energy. That thermal energy is conducted from the muscles into the bloodstream, warming up the blood a little bit, and the blood then transports that thermal energy around the body. That's a convective transport. Now, that blood would, say, for instance, transfer the thermal energy to the skin surface, where it could then be dissipated to the environment. Now, modeling convection is a bit more challenging than conduction, just because of the intricacies of the energy transfer and also the dynamics of the fluid. It's found that a good approximate model is as follows. Clearly, the rate of heat energy transfer should depend on the surface area in contact between the object and the fluid. It should depend on the temperature difference between the object and the fluid. And finally, there's a parameter that reflects how readily the surface transfers energy to the surroundings. So this involves the conduction somewhat of the thermal energy through the boundary layer, and then also how readily the fluid is able to move the energy away from the hot object. Let's do a simple example. We'll consider a person going outside on a cold day. Their skin temperature is 34, and the air temperature is 4 degrees. So the rate at which they lose energy to the air is given by h, the surface transfer coefficient, their surface area, and the temperature difference between skin and air. Now what happens in practice is that your body will warm up the air around it a little bit. That warmer air is less dense than the surrounding cold air, and the warm air will rise. So you can actually see a little heat plume rising away from your body if you look with sensitive infrared instruments. And then that warmer rising air is replaced by more colder air, which then again absorbs energy from your body. So there's a loss of body heat to the environment, and we calculate it in this way. Now a typical value for the surface transfer coefficient is about 10 watts per meter squared degree. So there is 10. Now a watt is a joule per second, so the units are there. That's watts per meter squared degree. We multiply by the surface area. Human body has about 1.5 square meters of surface area. That number was given here. And then the temperature difference, as we said, 34 for the skin and 4 for the surroundings. So this is the rate at which you're losing energy to the air. It's about 450 watts. So you're heating up the air around you, and that's rising just passively. This is called passive convection. And what happens, of course, if, say, the air is not still, and there's a wind blowing, is the surface transfer coefficient will get a little bit bigger, and then you're losing you're losing energy at a greater rate. And that's the example that we'll pick up in class. But for now, in still air, this is the rate at which you're losing energy to the environment. So there's a quick example of convection. Next, we consider the third and final means of transporting thermal energy, radiation. Oh, there's an example in class. There we go. Now, radiation is governed by what's known as the Stefan-Boltzmann Law of heat radiation, and we'll see that the rate of radiant energy transfer depends on what the surface is made of. And there's a parameter known as the emissivity that reflects that. We can just highlight that here. There we go. The rate of radiation from a surface depends on a parameter known as the emissivity. And so the emissivity is how much of the energy that hits the object actually gets absorbed into the inside and heats the object up. So if you had a 10% emissivity, that would mean that of the radiation hitting the object, only 10% actually warms up the interior. The other 90% just reflects off the surface. By contrast, a 0.7 or 70% emissivity object, that's absorbing 70% of the incident radiation and only reflecting 30%. Now, these two limits are characteristic. This 10% is characteristic of, say, a white reflective surface, and this 70% emissivity would be consistent with a darker surface, so that the actual surface treatment has a large impact on the emissivity, as does what the surface is made of. Now, we've seen already two means of transferring thermal energy, conduction and convection. In both cases, the rate of energy transfer depended on the surface area and the temperature difference for both convection and conduction. Now, there was also a constant involved. This is the surface transfer coefficient for convection, and then the conduction rate depended on the thermal conductivity and the thickness. So we would expect radiation would be similar in that it should depend on the surface area of the object and the temperature difference between the object and its surroundings, and then finally there should be a constant of some sort. So we would expect that the rate of energy transfer by radiation is some constant times the area times the temperature difference, as was the case for conduction and convection. What we find, though, when we do an experiment, and we can measure that rate of thermal radiation coming off an object, there are devices to measure that, spectrometers they're called, we find that the equation is actually a little different. Instead of just being linear first power temperature difference, it's actually a power law. It actually depends on the fourth power of the temperature difference. So it's the object to the fourth power and the surroundings temperature to the fourth power. There's the surface area. And then the constants, well, we said that it depends on the emissivity. Remember, that's whether it's white or black. And then the constant is known as Stefan's constant, and its value is 5.67 times 10 to the power minus 8. Now, it is per Kelvin to the power 4. In the other laws, it wouldn't matter whether you use Kelvin or centigrade because you're just finding a temperature difference. Here, it does matter, and we have to use Kelvin absolute temperatures in this calculation. Let's do a simple example. Let's say that you walk into a cool room, and your skin temperature is at 34 again, and the room is at 25. There's your surface area, and the skin actually has a fairly high emissivity. It emits radiation quite well. So we want to find the rate of radiation away from your body. So we will use the Stefan-Boltzmann Law, which says the rate depends on the fourth power temperature difference, or the difference between fourth power temperatures, the surface area, the emissivity, which is the surface condition, and then some constant that we determine experimentally. Now we must use Kelvin temperatures. So the skin temperature was 34. We add 273 to convert to Kelvin. The room temperature was 25. We add 273 to convert to Kelvin. Now we need to raise those to the fourth power, subtract then multiply by the surface area, which is 1.5 square meters, the emissivity, which is given as 0.9, and then Stefan's constant, 5.67 times 10 to the power minus 8 watts per meter squared, Kelvin to the 4th. Now in terms of the units, meters squared cancels, Kelvin to the 4th cancels, and we just end up with watts. That's good because, of course, this is a rate of energy. It should be watts. And the value we get is 76.2 watts. Now, an easy way to raise to the 4th power is just to squared. So I just like to show you that. 298 squared. So that's the difference between the two 4th power temperatures. We multiply by 1.5, we multiply by 0.9, then we multiply by Stefan's constant, E8 negative. And there you have our 76.3 watts, isn't it? And so that completes the picture then that we wanted to paint for you. Energy transfer by conduction, convection, and finally by radiation. We'll pick it up at that point in class and do another example of each of those.